Okay, so ready to begin. Yeah. So finally, we have a talk on class groups. So now we have the CG part. I guess the next one will be the NT part. So we will take care of the whole title, which Michelle's talk about the international. Okay, so today's this talk will be on the P ranks of the ideal class groups for imaginary quadratic fields by Jaitra. Chattopadhyay. Okay.
Thanks for the introduction. So I'd like to begin by thanking the organizers. For giving me this opportunity to speak here. So I have been a part of this ICCG and FRT in 2017 as well as in 2018. So it's a great pleasure for me to be back here at KSOM. So thanks for having me. So the title of my talk is on the P ranks of the ideal class groups of imaginary quadratic fields, and it's a joint work with Professor Anupam Saikia, who happens to be my postdoc mentor. So for a number field K, we denote the ideal class group usually by this notation CLK, and the order of this finite abelian group by the symbol HK. So in view of Gauss class number 1 conjecture for real quadratic fields that say that there are infinitely many real quadratic fields with class number equal to 1. So which is still unresolved till date. So we ask somewhat weaker question about the divisibility of class number. And almost 100 years ago, Nagel proved that there are infinitely many imaginary quadratic fields whose class number is given by a divisible by a given integer g. And this result has been proven for real quadratic fields in 1973 by Weinberger and reproved by many others. And later in 1984, it was proven for any number field of, any given degree by Ichimura and Azura. Okay. So let us come to the definition of the rank of a class group. So we first fix a positive integer n, and then the m rank of the class group is the number of is the largest integer r such that those many copies of Z mod mz are sitting inside the ideal class group. So that integer we call to be the m rank of the ideal class group. So it is clear from the definition that if the rank is at least 1, then the class number is divisible by m. So in some sense, the rank gives us more information rather than the divisibility of the class. Okay. So now the question is, how are these ranks distributed when we fix the degree of a number field and ask about the m ranks of number fields of a given degree? So a folklore conjecture is that the sequence of ranks is unbounded when we let the number field k vary over a certain fixed degree. And by Cohen-Lemster heuristics, the prediction is that there exists a positive proportion of quadratic fields with a given rank. And for for quadratic fields and r equal to 2 by genus theory, we can say that this is true. But for any integer r bigger than 2, nothing is known. So we kind of ask some quantitative questions from this point. So first we fix two integers m and n and denote this nm of this x. So what is this quantity? This counts the number of imaginary quadratic fields whose absolute discriminant is bounded above by x and the m rank of the ideal class group is at least m. And then we ask the natural question, what is the asymptotic behavior of this quantity as we allow x to go to infinity? So there are certain progress for certain particular values of m and n in recent years. For example, Luca and Pacelli, they proved that the number of imaginary quadratic fields whose ideal class group has 3 rank at least 2, that count is at least x to the 1/3, and it was recently proved in 2020 by Yang Yu that it can be improved up to x to the half minus epsilon for any epsilon positive lying between 0 and half. And then Levin and his collaborators proved that the number of imaginary quadratic fields whose 3 rank is at least 5, that has a lower bound of x to the 1/30 over log x. And there are similar such improvements like this. So we can see that the x to the 1/30 over log x can be improved up to x to the 1/15 over log x squared. So that's quite a lot of power saving improvement. And our result is kind of an improvement of the result proven by Bion, that the m rank is at least 2, which has a lower bound of x to the 1 over m minus epsilon. So we could prove that we can go up to x to the 1 over t minus 1 minus epsilon under the validity of the ABC conjecture. So in course of the talk, we will explain where exactly the necessity of applying ABC conjecture arises. Okay, so the precise statement is this, which is a joint work with Anupam here. So if t is a prime number bigger than or equal to 5, then the number of imaginary quadratic fields whose ideal class group has t rank at least 2, that has a lower bound of x to the 1 over t minus 1 minus epsilon. So our proof is based on the technique developed by Yang Yu. So let us briefly recall what he did. So his result shows that n3 of 2 of x is x, at least x to the half minus epsilon. So what he did is he kind of worked with a parametric family of imaginary quadratic fields and counted how many of these quadratic fields are there for which the parameters are coming out to be squared. So precisely what he did is he considered this multivariable polynomials fn comma a comma b, which is given by this expression, and counted the square free values of this polynomial. And once this value f of n comma a comma b is square free and we attach the square root of the negative of this to q, then he proved that under these two conditions, that ab is at least 1 and d is 4abn square and is square free, then q square root minus d has a class group whose 3 rank is at least 2. And we can see that if we fix a sufficiently large prime number q and vary these integers a b of order q cube, and if the quantity fq a b is square free, then it has 3 rank at least 2. It follows from this proposition. And the necessity of choosing q to be a prime, that is for some sort of a simplicity, but that doesn't play much role in it. So far we can see that if a and b are of order q to the 3, so in the expression 1 of fnab, we see that fnab is of order q to the 12. So that forces us to choose a prime q of the order x to the 1 over 12. So once we choose a prime q of this order and then count the number of integral tuples which lie between q to the 3 over 6 up to q to the 3 over 5, then we see that the resulting polynomial value is of order x, and we are interested in knowing how many of these can be realized as SQAB and are square free. So in other words, we define this quantity RT that counts the number of tuples that are of this form, that is lying between q to the 3/6 to q to the 3/5 and square free. So in other words, this is the counting function summation mu square d, where mu is the Mobius function, and d is allowed to go up to x, and the RT is strictly positive. So can you prove that this has a lower bound of x to the half minus epsilon, which proves this theorem. So we follow the same technique. So before embarking on the proof, let us recall what we are going to prove. So we prove that np2 of x is at least x to the 1/t minus 1 minus epsilon under the ABC conjecture. So we first start with a polynomial like this polynomial fnab and count the square free values of that polynomial. So in our case, the polynomial is fq of ab, that is given by this expression, and we choose a prime number first q, which is of order x to the p minus 2 upon 2p times p minus 1. So as you can see that if you take p to be 3, then this expression is coming out to be x to the 1/12. So this is kind of a generalization for used result for an arbitrary prime p. And then the two conditions are that if fqb is a square free integer and it is more than 4ab power t minus 1/2 times q power t plus 1/2, then the ideal class group of q square root minus fqab has p rank at least 2. That means it has a subgroup of the form z mod t direction z mod t. So now it remains us to see how many of these polynomials, these values, are square free. Okay. So let us first give a brief sketch of proof of this proposition. So we first let these quantities xi and yj like this, where our polynomial g is defined by this formula a to the p minus b to the p over a minus b. So once we define these four quantities x1, x2, y1, y2, we can see that this x1 square minus 4y1 to the p and x2 square minus 4y2 to the p, they are equal, and they are equal to minus fq of a. So from this equation, we see that for the choices of a and b as the suitable powers of x, the d is positive and of order x, and d is more than 4 times a times b to the p minus 1/2 and q times q to the p plus 1/2 for sufficiently large values of x. And then again from equation 2, we can see that xj plus square root minus d over 2, this principal ideal is coming out to be some aj power p, and we can prove that this aj, a1 and a2, they are non-principal. And it turns out that their pth powers is principal. Therefore, in the class group, they are elements of order p. And we showed that these two classes intersect trivially. Therefore, they give a subgroup isomorphic to z mod pz direction z mod pz. That proves that the proposition holds for z mod pz direction z mod pz. Now it remains to see how many of these values are square free. So these values are given like some values of a bivariate polynomial. So if we have to ensure that that is square free, there are two things that need to be checked. The first one is that the polynomial itself should be square free as a polynomial, that means as an element of qxy. And the second condition is that it should not be divisible by the square of any fixed prime. So even though it may be a square free element in qxy, it might happen that some square like 4 or 9 divides all the values. But we could show that for this choice of fqxy, these two conditions are satisfied. Therefore, we can have square free values of this form. So now recall that q was of this order x to the p minus 2 over 2p times p minus 1, and a and b were chosen in this suitable range. Then fqab is positive and fqab is of order x. So what we are interested in is looking at this set of lattice points a comma b that are in this range, and how often an integer d is realized as the functional value of fq. And then we define S1, which is this quantity which counts the how often that FQAB is coming out to be square free. And we define this auxiliary term S2. Now to estimate S1, we use a result of Bion-Conen that says that if we have a multivariable polynomial which satisfies these two conditions, that it's a square free as a polynomial and no certain square of a prime number divides all the values, then a positive proportion of values turn out to be square free. So using that, we could show that S1 has an upper bound of q to the 2p over p minus 2. And counting the number of duplications, we could show that S2 has an upper bound of q to the 2p over p minus 2 plus epsilon. So now the Cauchy-Schwarz inequality gives us this equation. So we have
That's not going to work.
okay. So we have a lower bound on the term on the right side, and we have an upper bound for the second term on the left side. So once we bring everything to the right side, keeping this mu d squared term to the left, then we see that whatever we needed, the summation d up to x and s is positive for mu squared d, that has a lower bound of x to the 1 over p minus 1 minus x. So this is the proof. So these are the references that we have used. So this talk was based on this third paper that recently appeared in the journal. And I would like to mention that Gilbert and Levin, they made a very good survey article that appeared in the conference proceedings. So we can have the history of these lower bounds and all from there as well.